Hello everybody and welcome back to our computer lab for the Power Programming class for your Unit 7. Now, in this unit, I would like to talk to you about and show you how you can efficiently speed up a program using shared memory. And when you are using shared memory to improve your speed, you want to be sure and careful about the potential hazards that come about with threads colliding essentially when they're um, writing or reading from or writing into the shared memory units that they are supposed to have access to. Now, I would like you to think about these three concepts that I'm going to cover in this lab, and this is going to be very, very helpful for you when you're working on your program for the next programming assignment, which is basically image blurring. One of the concepts, which actually you had as an extra credit question on your midterm, is when you would like to have multiple threads within multiple blocks of code, either two-dimensional or three-dimensional. How would you represent the indexing correctly from your block indices, block ID.x and block ID.y, and thread ID.x and thread ID.y into their location in the global memory, or for that matter into the shared memory as well. So that's one concept that I would like you to look at when we develop this program today. The second concept I would like you to look at is the concept of so actually let me just write these down for you. So as I said, one of the concepts that I will be covering today is essentially your indexing, or rather calculating your offset. When you have a a block or thread of memories, memory accesses, and so for example, if you take your data and then you break it into multiple blocks, and then each of these blocks will have their own sets of threads, then for each thread you would have a thread IDX dot x and dot y, and then you also will have your block index dot x and dot y. So one of the important aspects here is that when you're calculating the offset, so you basically have your global memory, and the addresses into this global memory, whether it's a one-dimensional or two-dimensional, it's always going to be essentially a one-dimensional offset. Because remember, when we define this, we're going to define, for example, something like an int pointer, device pointer, or something. So basically, this guy is going to be a one-dimensional data, whereas we have a two-dimensional or maybe even a three-dimensional block sets of grids, which will have two-dimensional or three-dimensional threads inside of them. So one of the ideas here is to map this block index and thread indices into essentially an offset. And I'll show you how to calculate this offset. So the first item that we're talking about here is indexing into your memory. The second item that I would like to talk about comes about with the question of, or rather, how you would basically define your shared memory and how this shared memory will be treated. In your CUDA program. How does your GPU treat blocks of shared memory? The idea basically is that when you create a shared memory, it's going to be a local set of memory items that will be dedicated to each block. So all threads within that same block will have one shared memory block, and they will work with each other on that shared memory block, and every other block will have their own copy of shared memory block, and their threads will work on their copies of shared memory there. And the third item that I would like you to look at specifically is what happens when threads step on each other's toes, and to basically look at your thread collision and what is bad about it and how to solve thread collision. So we want to see the problem here and then how to solve it. So these are the three concepts that we're going to be covering in today's lab, in this lab for Unit 7. It's actually a fairly simple program. And let me just run this program once for you, and then we'll go about and start writing this program. And specifically, first I show you the output of this program, and then I'm going to show you a little bit of a theory here to show you how this output comes to be and is calculated, and then how you can basically go ahead and write this program. So this is the program. I'll just go really quickly over, and I have some carryovers from, for example, the previous programs in here. So the basic component of this program is in the top here, we're going to define a dimension for our image. So in this case, I'm going to create like a 512 by 512 square image. You could change that to 1024, 2048, or whatever number you want. Then I'm going to define a K for the dimension of each block. So K is going to be how many threads are going to be in a block, and it's going to be K by K. So when K is 16, each block will contain 16 times 16, so that's 1024 threads in each block. Then I'm also defining a constant pi, essentially 3.1415, and then this is the body of my program, and the program basically calculates a two-dimensional image, and this two-dimensional image, essentially the color would be represented by an equation, and the equation is very, very simple. I'm calculating the sine of the x offset divided by a period by the sine of a y offset divided by a period. So this is going to be basically a kind of a sine form, and when you look at the image, it's going to look like a circle. So basically I'm trying to calculate the radius of a circle, or rather the if this were a two-dimensional image, the center of the circle to have the maximum number, and as you go away from the center, the intensity, the color of your image falls down, and at the border of that center, you're going to have 0. And I'm calculating this over my GPU. The main body of the program is fairly straightforward. As I said, I have carried over code. So here, just opening an image and doing stuff. Actually, let's just keep all these. I'm just going to comment all these out. Okay, so I commented out all the unnecessary things. So basically, I'm creating an image. I'm calling it the GPU image, and as I said, it's dimension by dimension. It's basically a colored image, so it's CV_8UC3. Then I call my CUDA function, which basically associates memory, creates memory, allocates memory on GPU, calls my kernel, and copies the data back, and then I'm showing the GPU results. And finally, here is my calculate with CUDA. It passes the image, it creates the data on the GPU, it associates the data, then creates a grid, creates a block, and calls my GPU DCT function on the image data, then some error checking code, and the results is going to be performed. So a fairly straightforward program, and this is not going to take a long time for us to write it. Let me show you the example. So when you run this program, the idea that I have here is that I would like for this image to calculate, for example, for the center of each block to have a square fitted in it. And so the square in this case, for example, is in the middle of each of these blocks in the image as you see. And to basically form a circle in that block. Now, as you can see here, this is not really a nice looking code. The problem is actually not the fact that I have these blocky pixelated results. That's fine. That is my code should actually create that. The problem is these colored random scattered artifacts in my image. This is caused by thread collision. Essentially, when a thread was writing into a block, another thread came in and attempted to write and just passed over. So the result is not looking nearly as good as it should. Here is how the image should look like. And as you notice, the problem is just one sync threads function call. That's the only difference that is happening and causing this artifacts, essentially causing the thread collision. So the result should look very nice, like what I have here, a very nice looking formatted image that essentially basically creates those circles. Now if you say why these circles look more like squares, it's because of my period, it's because of my scale of operation. So effectively, to make these look more circle-like, if I go ahead and make this scale factor 512, I have bigger but more circle-like results in my image. And so this is essentially how it looks like. So my circle is going to basically start from the center here, and as you go farther away from the center, it is going to look more like it's going to the intensity is going to fade away. So to make a bigger circle, if I increase my scale to 1024, basically making a finer calculation, I'm going to create much more circular format. So as you see here, I've got the center is pretty bright, and as you go away from the center, the intensity, the result is going to fade away and create this nice looking pattern. I can go ahead and increase the dimensions of my image as well, and so I'm going to get a bigger image. With a better looking circle calculation. And so, and of course, this is going to be repeated because the calculation I'm using uses sine functions, and sine functions are essentially periodic functions. So I'm going to have a replication of the circle farther away to the right. And of course, larger images, if my GPU memory allows for it, I'm going to get a much bigger image. And as you see, it's got a huge image that is represented. Let me then increase this value to 2048 to show you a finer circle. And so here is that huge image, 4096 by 4096, and the calculation of my values, as you see. So let's move back to a simpler, smaller set. I'm going to make this 128, the scale, and your book calls it period. Basically, the period of how many pixels is the period of your sine functions. And we're going to go back to a 512 by 512 image. And when you run this program, you see that you've got each circle now look more like blocked squares, of course. But each circle basically starts, and the period is going to be on 128 pixels wide in X and Y, and the calculations are performed. So now let's start writing our program. And what I'm going to do with this program, I'm going to start up again from a CUDA um, code, a CUDA template, and rework this program just again to give you another experiment or experience with creating code that work with CUDA GPU and CUDA CPU and OpenCV CPU functionalities. So if you are completely familiar with how to set these up, you may skip to where we're going to start the programming. Essentially, it's going to be in the next video. But so this first video, I'm going to again show you how to start up from an empty project from scratch and redo, or rather get rid of all the code that is unnecessary in your program and add your own code here. Alright, so here we are in our Visual Studio environment. So I'm going to go again, as I said, create a new CUDA project and add OpenCV libraries so that we could use and show our images and so forth. So we're going to go into File, New Project, and then from there we are going to add a CUDA project, and let's call this CUDA underscore circles shared memory. And I'm going to go and add it into my project folder, CUDA OpenCV projects, and click OK. So your compiler is going to create your CUDA template for you. Before we do anything, I'm just going to go ahead and change this add with CUDA to GPU circles with shared, and I'm going to delete all the references to it. Well, actually, let's pass to this this function a rather, let's call this calculate with GPU. So GPU calc image, and I'm going to pass a mat reference to it, and we'll see later on how we can fix this problem. Then let's call this GPU with shared memory, and it will take an unsigned char pointer, and I'll call this destination, and it also gets a constant unsigned char pointer, and let's call this a actually just an unsigned constant char pointer should be fine. So we're just going to make the kernel to calculate and to accept an unsigned, oops, typo, an unsigned char pointer destination. And it's for now my code will be empty, and so in my main I'm going to clear up everything. I'm going to basically keep create a CUDA status, and from there I'm going to delete everything else all the way down to CUDA reset device. Cool. And then I'm going to basically make my add function and rename it and pass to it a mat reference my image, and create an unsigned char for my device pointer. I'm going to call this device PTR. I'll set a CUDA status. Alright, CUDA device reset, CUDA malloc. I'm going to call this my PTR. Actually, let me just eliminate all my allocations. I'm going to add these later on. And then same with my mem copies. This is going to be my kernel. And CUDA device synchronize. I'm going to keep that. I'm going to delete everything else. And this was called device PTR. And so, do I have my CUDA status? No, I don't. Yes, I do. Okay. Alright. So, this is basically all I have so far. So this is my empty program shell here. Now, what I need to do is to make this program use my OpenCV materials as well. Now, the problem is, as you see here, the mat is not recognized because it is a OpenCV object. So I'm going to right click on my project, go to properties. Remember, there are 3 steps we need to take. We need to add the header files, we need to add the library folders and the library files, and we need to add our executable folder to the debugging path. Alright, so the first step in me to be able to use my OpenCV is to add the header files directory of my OpenCV to my project. So to do that, we're going to go and find the location of where the include files are. Now, in order for me to be able to do my C++ related header files, I need to have access to C++. Here, I only have access to CUDA C++. So I need to add to my project a CPP file. So click on Add, New Item, and C++ file, and let's call this temp. Now, you don't have to add anything to the temp. Just the fact that we added a C++ project here, or C++ file to our project, we will now, from our project properties, get access to C++ properties. So click on C++ properties, and then open, or rather edit the additional include libraries. And here I need to add my additional include files so that I'll be able to add the location for where my header files for OpenCV are. So click on Open, and here I'm going to basically type in C backslash, I guess I'm calling these gaming programs, OpenCV, build, include. When I add my include files, just like I did here, and I go back to my CUDA, then I will be able to add my include header files. So I'm going to go and add OpenCV /cv.h and include OpenCV /hi GUI.h. These two libraries will get me basically the materials I need, the functionalities of OpenCV, like mat, imshow, imread, imwrite, and a whole bunch of functionalities with OpenCV. Before I'm able to use these, I need to add the namespaces to my project. So I'm going to add using namespace CV. When you add namespace CV, as you see automatically here, the mat, which is an object from OpenCV libraries, is going to be added to your project, so you can now use objects of mat kind. So now I'm going to scroll down to make sure that I'm not going to get any kind of compile error, and I am not. So let's press F7 to compile. Okay, my project succeeded. As you see here, it's because I don't have any kind of compile error or compile problems here. So now the next step for me is to go ahead and make sure that my OpenCV works. In order to do that, I'm going to create an image, and I'm going to call this image GPU image. So in main, up here, right after I created my CUDA status, I'm going to create a mat GPU image. And actually, before I do this, let's go ahead and define some basic structures here so that I could use them. So I need to create a structure that determines the size of my image or the dimension of my image. So I'm going to do define dim, and let's make this dimension 512. Also, I'm going to define pi 3.141592692, because I'm going to use pi later on in my project. Furthermore, let's define the size of the blocks that I'm going to use. So I'm going to basically define K, and for now let's make K 16. A block of 16 by 16 threads. We're going to see these later on in our project. Let's go back to our main function, and in the main function I'm going to create a mat, and I'm going to call that GPU image, and it's the size dim, comma dim, and that's number of rows, number of columns, and I'm going to make this in a CV underscore 8UC3. Basically, this is going to be, each pixel is going to be RGB. R for red, G for green, B for blue, and RGB is going to be red, green, blue. Each of them are going to be 8 bit, which is going to be 1 byte. So I'm going to have an 8 byte unsigned character, and I'm going to have 3 of those for R, G, and B. Okay, so that's my my GPU mat. Let's compile and make sure that this works. Okay, I've got a problem. Let's see what that problem refers to. Okay, these look like linker issues. So since I have linker issues because I created an image, but I don't have access to my OpenCV libraries, linked libraries, I'm going to have to go back to my project properties, and under the project properties we added our header files. So now we need to add our linker files as well. So the second step in making the OpenCV compile and run is to add linker folders and files. So go to the linker in the general section of the linker. We'll do now the second step. The second step is to add our linked folders. So it's going to be in C, open, I think I call this gaming programs, OpenCV, build, and since I'm under 32-bit platform, I'm going to go x86 vc10 \lib. This will add the libraries folders for my Visual Studio 2010. So if you're using Visual Studio 2012, you go VC11, and if you're using Visual Studio 2013, you add VC12 for 32-bit. For 64-bit, so I'm using 32-bit here, so I'm going to use x86. If you want 64-bit platform, then you're going to do 64 here. Now that that's added, I need to add my lib files as well. So the lib files that I'm going to add, so click on open and then edit, and then here the lib files that I'm going to add are going to be open CV. Let's see, actually I don't remember what they were, so I'm going to open up a my programs, then go to gaming programs, C, gaming programs, OpenCV, build, x86, VC10, lib, and the ones that I'm going to use are going to be OpenCV underscore high GUI 247d.lib and OpenCV core 247d.lib. So I'm going to add those, OpenCV underscore core 247d.lib and OpenCV underscore high GUI 247d.lib. Now, if you have my OpenCV is version 2.47, yours might be 2.48, 2.40, whatever. And since I'm working with the debug here, my active configuration is debug. I add the D, and remember it has to be the whole file name. So again, just let's double check and make sure that all these names are good. So OpenCV underscore core 247d.lib and OpenCV underscore high GUI 247d.lib. So my files are also added, and my linked files. And now let's see if we get any link errors. So now that I added my library files, now this file, the mat GPU image that I'm creating, since now this requires a binary, it's able to to resolve the external links, the external libraries, essentially. All right, so now I have my matrix created here, and now let's just show it. So I'm going to basically do an imshow, and I need to give it a window name. I'm going to call it results, comma GPU image. Now this should compile, and I should have no problem with the performance here. Okay, it succeeded. Now if I attempt to run this program, my runtime would tell me that it could not find the dynamically linked library. Remember, when you added the lib files, you're basically essentially helping your program compile, but it cannot execute because the binary file, the DLL file, is missing, and OpenCV underscore core 247d is missing. The problem can be fixed by adding the location of your binary files of your OpenCV to your project. So to do that, now we do the third step. So the third step in finally getting the program compile and run is to add the location of your lib files of binary folder of your OpenCV to your debugging in project properties. So we go to debugging, and under the debugging we need to go to the working directory. Right now my executable files are going to run from my project directory, but my DLL files for OpenCV are somewhere else. So I'm going to add that location to the location of my my executables. So where they are now, this time I'm going to show you the alternative way. You click on browse and you go on C. It was under gaming programs, OpenCV, build, x86, VC10, binary. The bin folder is the folder that we're going to have to use. So C colon / gaming programs, OpenCV build x86 VC10 bin is the location where my DLL files are. Now if I execute this program, it is going to run. It ran and it really quickly closed my image. So what I'm going to do is I'm going to add a CV wait. CV wait key. CV wait key is essentially a delay that waits for you to press a key on a keyboard. You could add a number, and if the number is more than 0, that's going to be how many milliseconds it's going to wait or inject the delay into your program. If you put 0, then it's going to wait for a key to be pressed. So if I execute this program now, it's going to execute. And it's going to show you the image that was created. So when this image was created, it was filled with a grayscale value, and that is going to be blank, and it's going to show you a blank kind of a gray image. So this is it for setting up your project. So so in the next video, I'm going to show you how to program this image. So the video unit 7, lab 2 is going to show you how to program our shared memory access pattern.